Human labor. Machines. Replacing human labor with machines. Performing round the clock in hazardous or unpleasant environments. Automation. Freeing people from unsafe or undesirable occupations. Recently, new possibilities for manufacturing automation have been created by the rapidly improving performance and cost characteristics of computers. The integration of computer applications within the various phases of manufacturing has led to the concept of computer integrated manufacturing. Computer integrated manufacturing, or CIM, is an approach which considers the manufacturing system as a whole, rather than as a set of independent functions. In CIM, computers participate in virtually all manufacturing activities and serve as the agents for integration through shared databases and communication networks. At the University of Iowa College of Engineering, laboratory experience is vital in educating industrial engineering students in the principles of computer integrated manufacturing. This presentation parallels the elements of computer integrated manufacturing as implemented in the laboratory and in industry. The elements of computer integrated manufacturing systems may be divided into three main areas: product design, manufacturing, and production management. Computers are used in several ways to support product design. One is geometric modeling. The part geometry is displayed on a computer screen, and with the appropriate software, the design engineer is able to create a graphical model of the object and make changes as needed. Most computer-aided design systems also support part dimensioning, tolerancing, and specification of surface finish, as well as identifying information in the body of the drawing. Most of the features of computer-aided design systems may be implemented in low-cost personal computers for use in the laboratory, as well as actual product design. Computers assist engineering design by supporting design databases. A key concept is group technology. Parts are classified into groups or families according to significant attributes, such as their geometry, the manufacturing process, or raw material. When a new part is designed, it is possible to search the database for a similar part and make minor modifications in its design. The classification is performed through an interactive dialogue that requires part information and assigns a code to each part. It includes external and internal shapes, dimensions, any threads, grooves, and splines, type of raw material, surface finish, tolerance requirements, and other manufacturing attributes. Group technology may also be applied to improve plant layout by grouping into a single cell the machines that are used by a given part family. Manufacturing is the process of converting raw materials, labor, and other inputs into finished products. Three main manufacturing activities can be automated with computers: fabrication, materials handling, and assembly. Fabrication consists of transforming raw material through processes such as turning, milling, drilling, pressing, extrusion, etc. These operations are performed with different types of machines which are likely to be operated automatically. Numerical control is a form of automation based on programs that control the operation of the machine tool. In modern NC systems, the control unit is a computer. The systems, called CNC for Computer Numerical Control, provide better performance by virtue of the great flexibility and speed of the computer. In the laboratory, tabletop machine tools retrofitted as CNC are controlled from a personal computer. The computer translates the part program into digital signals that are fed to stepper motors on the machines. The stepper motors control the positioning of the cutting tool with respect to the stock. The computer supports additional functions such as offline programming, program editing and verification, and links with CAD databases to allow automatic program generation from part geometry. Also possible are smart editor programs which check part program statements for syntax and logic errors prior to attempting execution. The part program may be executed on the machine tool or stored on tape or disk for future use. The materials handling function may be automated with automatic vehicles capable of moving around in the plant and transporting materials between workstations. Automated guided vehicles, or AGVs, may be guided by chain drives under the floor surface, magnetic stripes, or signals transmitted in wires on the floor. The laboratory includes a scale model of an AGV that can follow bright tracks on a dark background. The AGV has a scanning mirror to focus environmental light on a photosensitive element. The signals are processed by a host computer, providing vision for navigation. Another form of automation in materials handling are automated storage and retrieval systems. The computer controls the mechanism which accesses storage cells and maintains an inventory of parts, their location and quantity. Here, storage racks are mounted on rotating carousels, which are brought to the retrieving mechanism. This storage system is complemented with smart conveyors. Conveyors which are able to recognize the parts they carry and route them accordingly. A scale model of a sorting conveyor has been constructed in the laboratory. Parts are loaded on the conveyor by a robot from a gravity-fed chute. As the parts travel on the conveyor, they pass in front of several light-sensitive detectors. When the part interrupts a light beam aimed at the detector, an electronic signal is generated, amplified, and processed by a programmable controller. The length of the part is determined by the amount of time the beam of light is interrupted. The controller then decides at which of the three chutes the part will be ejected. A configuration of numerically controlled machine tools interconnected by a material handling system and operated under central computer control is known as a flexible manufacturing system, FMS. FMS offers flexibility in the types of products that the system can produce and in the production rates. The machine centers are capable of performing several operations such as drilling, boring, grinding, etc., on different parts belonging to the same group technology family. Part programs and tool selection instructions are downloaded from the central computer to the machine center when the workpiece is delivered by the materials handling system. Once processing is completed, the machine center notifies the central computer, which then dispatches an AGV to pick up the workpiece and deliver it to the next station. The central computer schedules the flow of parts through the system, efficiently utilizing the machining centers. It monitors tool wear, alerts the operators when tool replacement is required, and is capable of rerouting pieces in case of work center failure. Assembly automation utilizes the capability of robots. Industrial robots are general-purpose programmable machines capable of performing a variety of tasks such as picking and placing, painting, welding, etc. Most robots have an arm that operates from a static base. In the lab, articulated robots driven by stepper motors are programmed and controlled with a teach pendant or from a host computer through a communication link. Each robot has an onboard microprocessor that interprets the incoming commands and translates them into pulses to the stepper motors that control the various joints. The use of a host computer allows offline programming, program verification, editing and simulation, as well as maintaining a database of programs on magnetic media. A mobile laboratory robot with an arm may serve as an AGV and perform loading and unloading operations independently. This robot can navigate with the aid of light, motion, and sound detectors connected to its central processing unit, or CPU. Robots must be able to react to changing environmental conditions in order to successfully substitute human labor. The sense of vision is a major source of information for human operators. With the use of computers and appropriate mathematical techniques, it's possible to achieve a degree of vision in robots. The first step in computer vision involves the capture of light intensity and color information in the environment. This is accomplished with a video camera. A scanning electron beam falling on a photosensitive surface generates an analog signal. This signal is then sampled and digitized into a number of discrete levels depending on the resolution of the system. Light intensity thresholds control the range and sensitivity of the digitized image. By adjusting the thresholds, we may filter the image captured and eliminate noise, facilitating further processing toward recognition. Computer vision may be used for inspection, navigation, or to assist robots in performing assembly tasks. An instructional program which simulates computer vision illustrates the remaining steps: image filtering, edge detection, segmentation, and classification. Production management is concerned with the optimal performance of the entire manufacturing system. It includes the following areas: inventory control, quality assurance, capacity planning, job scheduling and routing, facilities layout, work center design, and line balancing. MyFlag is an interactive package that assists in optimizing plant layout. The input consists of the types and sizes of departments needed and the measures of material flow between them. The program generates a proposed solution which is displayed graphically. The analyst may examine the initial solution and attempt to improve it. HALB is a package designed to assist in the allocation of tasks to workstations, known as assembly line balancing. The program applies heuristic rules to generate a near-optimal solution. The analyst may interact with the program and direct the solution to account for factors not reflected in the heuristics. The graphics capabilities of the personal computer are used to enhance the dialogue between the machine and the human problem solver. Throughout the various fabrication and assembly stages, various tests and inspections are performed to ensure that the product conforms to quality specifications. Computers can be connected to various test and sensing devices to capture data about the relevant variables. The results may be displayed on the video display unit, printed, or used to generate voice output to alert the operators immediately when situations are out of control.
Processing is out of control.
Design, manufacturing, and production management are three central activities in virtually any manufacturing organization. However, they require the support of other functions: purchasing, accounting, finance, personnel, marketing, maintenance, strategic planning, data processing, and administration. The information needs of all these functions are highly intertwined. The computer is the agent of integration and is supported by two technologies: data-based management systems, that is, software which facilitates access to large amounts of data contained in interrelated files of different types, and communication networks, which allow different types of computer-based equipment to communicate with each other and with a central database. The nodes in a communication network consist of machine centers, AGVs, robots, and other machines, as well as designers, engineers, accountants, managers, and other information workers. Computer-integrated manufacturing is being adopted by manufacturing organizations which are striving for success in the light of strong national and international competition. Computer applications in product design, manufacturing, and production management are the building blocks of computer-integrated manufacturing systems. The practical education of engineering students in the elements of computer-integrated manufacturing prepares them to contribute to the effort of improving productivity and quality in the modern factory.